Hello, my name is Andra, and I am very excited to introduce the project Turning Bog Iron Ore into Gold, which revives the historical craft of iron metallurgy in Lithuania. Over the past several years, we have combined education with hands-on experimentation. Our activities include not only impressive iron smelting demonstrations in the spirit of living history, but we also conduct scientific testing, metallographic research to evaluate the efficiency of our smeltings and compare our result with archaeological findings. So in this presentation, I will first discuss the type of ore available to us. Then I will outline the smelting parameters used, and finally I will present the outcomes from our 10 experimental runs. Project takes place in a region with bog iron ore deposits at various stages of formation, characterized by differing iron concentration and high phosphorus content. For our experiments, we selected a solid, relatively dense material containing over 60% iron oxide. Although this is below the minimum threshold for Bloomery iron smelting, which considered to be around 80%, according to Radomir Planer. But recent experimental smelting across various countries has indicated that bog iron ores with iron content as low as 50% may still be suitable for Bloomery iron production. Among the parameters used, one remained constant, the ore source. The others varied, including furnace type, fuel to ore ratio, blowing method and temperature, flux addition, and ore fineness. While our initial plan was to modify only one parameter per experiment, in practice, several factors were often adjusted simultaneously. The furnace sizes were determined based on archaeological data. We used two types of furnaces, one with a slag pit below the shaft and another with a discharge hole, similar to what is shown in this video. With prepared materials, an experienced operator could set it up in about 4 hours. Before smelting, the ore was roasted to slightly enhance its iron content. And for our initial experiments, we used coarse ore that had been only lightly crushed. During the initial experiments with tapping furnaces, the tapping slag was very viscous. No phyllite or wustite, typical of archaeological slags, was detected, suggesting that some iron remained in its trivalent form due to inadequate reducing conditions. Phyllite requires divalent iron, which was lacking, resulting in predominantly glassy and greenish slag. While rapid air cooling contributed to this, the slag composition was likely the primary factor because the iron content in the slag was significantly lower than that found in archaeological slags. And speaking of metallic iron, smelting 11 kilos of phosphorus-rich ore resulted in only 3 100 grams of phosphorus-rich iron in the form of such small pearls. To promote slag flow, we initially intensified the blowing and raised temperature. However, higher temperatures can lead to excessive carbon in the iron, even resulting in cast iron formation. Additionally, strong blowing and elevated temperatures increase the phosphorus content in the iron. To prevent iron carburization, we implemented countermeasures, such as reducing the fuel-to-ore ratio. Despite these adjustments, the slag viscosity remained unchanged, and it did not flow out of the furnace, while the amount of iron pearls even decreased. Then we reduced the blowing intensity and introduced slag lime powder as a flux to lower the melting temperature and viscosity of the slag. This is particularly important for phosphorus-rich ores, since calcium helps prevent phosphorus from transferring to iron. In the first trial, a 5% addition of flux decreased the temperature, resulting in less viscous slag that still retained its green color. In the subsequent trial, we halved the flux amount while increasing the air supply, which improved slag flow, but still resulted in insufficient iron content and lacked the desired structural and compositional features of archaeological slags. Phosphorus retention in the slag increased slightly, but the iron remained phosphorus-rich. In the next trial, we aimed to maintain the lowest possible temperature, noting that iron oxide reduced at 150 degrees Celsius, making higher temperatures unnecessary. The smelting temperature was kept around 1000 degrees, increasing only at the end. We also removed the turriere, creating a 10 centimeter diameter hole to simulate natural air supply. During this trial, the burden residence time nearly doubled, averaging 25 minutes. Unfortunately, the strategy failed, yielding no iron production, just a small amount of slag and a significant quantity of unburned charcoal and under-reduced ore. Subsequently, a series of trials were conducted using slag pit furnaces. The Bloomery shaft design remained unchanged, but we added a 25 centimeter deep, 30 centimeter diameter pit beneath it, where raw sticks were placed. And after completing the smelting, we discovered a slag block weighing approximately 8 kilos from 10 kilos of ore. The slag was metallic gray rather than green and contained contained more elemental iron in the divalent form, indicating more reducing conditions. The structure resembled archaeological slags and showed properties of phyllite. However, the iron remained phosphorus-rich, with some areas unevenly carburized, while others displayed characteristic of cast iron. During an additional trial, we crushed the ore into 1 to 2 centimeter pieces and mixed it with sideretic ore at a 1-to-1 ratio. The resulting slag was not green and had the highest iron content, comparable to amounts found in archaeological slag. The elemental composition and microstructure of the slag were also similar to those of archaeological slags, containing phyllite and wastite phases. And here you can see slag from this last experiment and can compare it to that from the previous tests. Speaking of metallic iron, phosphorus didn't transfer into it with only a small amount determined. In the last one, we returned slag tapping furnace with a 1-to-1 fuel to ore ratio using very finely ground ore up to 5 millimeters. Mechanically, the smelting was the smoothest, yielding the largest amount of smelted ore, about 14 kilos. The tapping slag was non-viscous, though its greenish color indicates that the issue of a reducing environment persists. The carburization of the metal was heterogeneous, but not very intense, with a low phosphorus content. So, after conducting 10 smelting experiments with ore from the same deposit, identifying the variables that most effectively reproduce archaeological material remains challenging. The viscous and green color slag from the slag tapping furnaces didn't resemble archaeological waste, indicating that the smelting conditions were not sufficiently reducing. In the case of furnaces with slag pits, more efficient smelting was observed. The slag's properties, its form, composition, and structure were closer to archaeological slags, indicating that this type of furnace supported better reducing conditions. Regardless of the flux used, the iron remained phosphorus-rich in both types of furnaces. Additionally, increasing the fuel-to-ore ratio in slag pit furnaces led to uneven carburization, including cast iron formation. In 2 experiments, one using a mixture of ores and the other smelting very finely ground bog iron ore, the results were positive. Wrought iron was produced and the slag structure closely resembled archaeological slags. These successful trials suggest that the mineral raw material and its preparation, particularly fine grinding, play a key role in achieving desirable outcomes. And these observations provide important guidelines for our future experiments, highlighting areas where adjustments can be made to improve smelting efficiency and the quality of the produced metal. Thank you for your attention.